Welcome to the second video of the week in Advanced Classical Mechanics. Today we are going to go over some examples of how the Lagrange approach can be applied to systems with constraints. The Newtonian approach can be applied fairly easy to some of these problems, but for others not so much. The first example we will look at will be of Atwood's machine, which can be used to determine the gravitational acceleration. So here's the basic setup. We have a frictionless, massless pulley from which we hang two masses, mass m1 and mass m2. We're going to measure the distance from the center of the pulley down to mass 1 as x. The question that we are asked to answer in this problem is, what is x double dot? In other words, what is the acceleration of that mass m1? That, of course, is going to depend upon the difference between the two different masses, m1 and m2. If mass m1 is heavier, then of course it's going to descend while it pulls mass m2 upward. And the rate at which it descends, or the acceleration downward, is going to depend upon that difference as well from an intuitive point of view. Okay, so to proceed on this problem, we will need to also be able to measure the distance from the pulley down along the string to m2. So we're going to label that as the distance y. And another important parameter for us will be the potential energy. Of course, we'll need that to form the Lagrangian. And we're going to set the potential energy when the mass is mass m1 or m2 are right at the same level as a pulley as being equal to 0. So we do our usual thing here. We're going to determine the kinetic energy, the potential energy, and from those form the Lagrangian, and then, of course, determine Lagrange's equations. First, we need to relate the lengths of the different strings to masses m1 and m2, and of course, the total string length doesn't change, so we're going to set x plus y to be equal to a constant. Doing so is going to allow us to use a single coordinate for this problem, and of course, it will be our natural coordinate, in fact, for this particular problem. We can take the time derivative of both sides of this equation and rearrange it to find that y dot is equal to negative x dot. In other words, whatever the downward speed is of mass m1, that will equal the negative of the speed of mass m2. Okay, with this being the case, we can quickly write down the kinetic energy equation. It will have T being 1/2 mv squared for each of the two different masses, with, of course, their respective speeds. So T is going to be 1/2 m1 times x dot squared, plus 1/2 m2 times y dot squared. We're going to immediately eliminate that y dot using the equation just above it. Y dot is equal to negative x dot. Of course, when we square that, the negative sign goes away, and so we're left with a total kinetic energy of 1/2 m1 plus m2 all times x dot squared. That's it for the kinetic energy. We now need to know what the potential energy is. So the potential energy equation is just going to be the sum of the potential energies for each of these different masses. It will be given by the usual potential energy equation, where the potential energy is equal to mgh. We have to take into account that the potential energy will be taken to be 0 at the height of the pulley. So the potential energy U will be negative m1 g times x minus m2 g times y. Again, we can substitute in for y. When we do so and collect terms, we find that the potential energy U is equal to negative m1 minus m2 times gx plus some constant. That constant actually isn't going to matter for us in the end, of course, because we will be taking derivatives of the potential energy, so it will go away. Okay, so we have the kinetic energy, we have the potential energy, and from this, using the standard Lagrangian approach, we can calculate the Lagrangian itself. It's just the difference between the kinetic energy and the potential energy. So we substitute from the two equations on the previous slide, and we find this gives 1/2 m1 plus m2 times x dot squared plus m1 minus m2 times gx plus some constant. Okay, now we write down Lagrange's equation, Really, all the hard work is done at this point. We'll see that will be in common with the rest of the problems, of course, as well. We write down the Lagrangian. We have a single coordinate that we're worried about, and that is x. So our Lagrange's equation becomes dl by dx being equal to d by dt operating on dl by dx dot. The substitution is straightforward. We take those derivatives and we find that it yields m1 minus m2 times g is equal to m1 plus m2 times x double dot. Here, x double dot, of course, is the acceleration of mass m1 as it descends. We take this equation and rearrange it for x double dot, and we find that it's equal to m1 minus m2 over m1 plus m2 times the gravity g. So at this point, we won't go on and actually solve this. Instead, what we'll do is take a look at equations of motion, such as the one we just derived, and try to understand what they're telling us. So what we see here is that the acceleration is going to be some constant factor, m1 minus m2 divided by m1 plus m2, times our gravitational acceleration g. So if we take two masses that are fairly close together, not exactly the same, mind you, we don't want a balanced situation, but we want them to be fairly close together, then the constant hanging out in front of g is going to be a fairly small number. In other words, we can expect our mass m1 to descend at some fraction of the gravity g. So this gives us a nice means, in fact, to measure the gravity g, because normally if we just held an object and we dropped it, it would be very, very difficult for us to actually measure the rate of acceleration. On the other hand, if we cleverly set up our two different masses so that it descends slowly, then in fact we reasonably can in the laboratory measure the acceleration as it's going downward, and then of course through our equation of motion here, that will give us the gravity g. So a really beautiful, I think, demonstration of the Lagrangian approach. It's also a beautiful historical experiment in physics that allowed some of the first really good estimates of the gravitational acceleration g. Okay, so just our summary statement here is the acceleration of our mass m1 is a fraction of the gravitational acceleration g. So a pretty straightforward problem involving Lagrangian mechanics. You could, of course, apply the Newtonian approach to this in a fairly straightforward manner. Now let's move on to some other problems where we'll up the difficulty, but we'll see that the Lagrange approach, in fact, handles them in a fairly straightforward and elegant, I think, way. The next problem we will look at is constrained motion on a cylinder. So we have our cylinder. It is sitting on this z-axis, and we'll imagine that we have some mass m that's constrained to move on the surface of that cylinder. So it must everywhere move on the surface of it, but it can't come off of the surface of it. Now we're going to suppose that between the mass m and the origin, which I've marked in right there, that there is going to be, say, a spring. We'll imagine that there is at the very least a Hooke's law force pulling that mass back toward the origin. So this force, of course, is what is going to keep the mass constrained to the surface of that cylinder. The question we are asked then is to find the equations of motion and describe the motion. So again, we're not going to end up solving the equations of motion here, but rather we will inspect that equation of motion, or equations of motion in this case, and obtain some insights from it. Okay, so how do we do this? Well, we're going to solve this problem in cylindrical coordinates. These are the coordinates that are natural for this particular system. In other words, we will use coordinates rho, phi, and z. So let's mark in those coordinates. Of course, z is already marked in. We will make a vector going from the origin to our mass m, and we're going to label that as the position or displacement vector r. We then will project that vector onto, first of all, the surface of the cylinder, but then also into the horizontal plane through the origin. So that will give us a triangle that looks like what we've shown right here. The lower arm of that triangle is, of course, the coordinate rho. It's also going to be equal to the radius of the cylinder. So we'll take the radius of the cylinder being the radius r. The coordinate rho is not going to vary. It's going to be an invariant parameter in our problem. Okay, we'll also need to know the azimuth, which we will label as phi. I've just drawn a line here that arbitrarily sticks out in the horizontal plane through the origin, and here we have that angle phi being measured. So we need to do the usual things here. We need to calculate or determine an equation for the kinetic energy. Then we need to do the same for the potential energy, form the Lagrangian, and then, of course, write down our Lagrange's equations. Now, in order to write down the kinetic energy, we're going to need to know the squared speed of the particle. So we'll have to use the different speed components that we have in cylindrical coordinates. So the speed squared is, of course, just going to be the rho component of the speed squared plus the phi component of the speed squared plus the z component of the speed squared. Now we know that rho is just going to be some constant r. So in fact, v rho is going to end up being 0. So the only two speed components we need to worry about are the phi and the z components. And those respectively give us r squared, phi dot squared, and z dot squared. So we know, for example, that vz is just equal to z dot. V phi, on the other hand, is going to equal the radius of the motion multiplied by the azimuthal speed phi dot. So that's going to be the product, r phi dot. When we square that, that's where we get r squared phi dot squared. Now that we have that, we can write down the equation for the kinetic energy. The kinetic energy is just T being equal to 1/2 mv squared. We substitute in from the equation above, and we find that our kinetic energy is 1/2 m times r squared phi dot squared plus z dot squared, I should say. That's it for the kinetic energy. We now have that expressed using two different coordinates, phi and z. We now write down the potential energy. Now, the potential energy we take from Hooke's law, and the Hooke's law potential energy is 1/2 k r squared, where r is going to be the distance that our string is stretched. So it, of course, is just going to be the distance from the origin to our mass m, and k is our Hooke's law constant. We can substitute in for r squared just using Pythagoras, and we find that the potential energy U is equal to 1/2 k times r squared plus z squared. We now have both the kinetic and potential energies, and so we can write down the Lagrangian L, which is just equal to T minus U. We substitute in for T and U, and we find the Lagrangian is 1/2 m times r squared phi dot squared plus z dot squared minus 1/2 k times r squared plus z squared. At this point, all the hard work really is done. All we need to do now is write down Lagrange's equations and turn the crank. So we have two different coordinates that we're concerned with, phi and z. I'll deal with z first. So Lagrange's equation for the z coordinate will have di L by di z being equal to d by dt of di L by di z dot. For the phi coordinate, we will have di L by di phi being equal to d by dt of di L by di phi dot. So we take our Lagrangian, we substitute it in, and this will give us the equations of motion that we need to understand how this particle is going to move along the surface of this cylinder. So we'll do the substitutions first into the z Lagrange equation. When we do the substitution and take the derivatives, of course you should verify all of these derivatives for yourself. We find we get the equation negative kz being equal to mz dot squared. We can rearrange that, and that gives us z double dot being equal to negative k over m times z. Now, we've seen equations like this before. This, of course, is just the equation for harmonic motion. So it turns out in the vertical direction, our mass m is going to undergo harmonic motion. It's going to oscillate up and down the surface of this cylinder. So that's just the z direction. Of course, we're going to need to look at the azimuthal direction as well, the phi direction. So to do that, we will substitute our Lagrangian into Lagrange's equation for phi. When we do that, the left-hand side derivative conveniently goes to 0, and that's going to be equal to d by dt of mr squared phi dot. Of course, this tells us that mr squared phi dot is a constant of the motion, so we'll summarize that as mr squared phi dot being equal to a constant. Now, you should recognize mr squared phi dot. This, of course, is just the vertical component of the angular momentum. So what we find here is that that vertical component of the angular momentum is conserved, and this tells us that angular speed is constant. Now, if you don't recognize that as being the vertical component of the angular momentum, then I encourage you to calculate the angular momentum using the vector L, angular momentum, being equal to the vector r crossed with the linear momentum p vector. So L is equal to r cross p. So take that r cross p, find the vertical component, and you'll get exactly what I've said here, m times r squared times phi dot. Okay, so we now actually understand this motion really well. Our mass is going to go around and around the cylinder. As it does, however, it's really hard to do this with your hand, but it will go through an oscillation, there we go, as it's going around and around and around this cylinder. And that makes pretty good sense. The spring, of course, is attracting it or pulling it constantly back toward the origin. We're going to conserve momentum as we're going around, so it's in fact continuing around this cylinder at a constant angular speed. Okay, so I think a really nice result. Some different observations here. Very nice that we got these two separate equations that allowed us to separately determine what's going on in the vertical direction and what's going on in the azimuthal or phi direction. It, of course, was fairly straightforward for us to understand that it was harmonic motion in the vertical direction. The really nice thing here is that conservation of angular momentum really came out very naturally from the whole Lagrangian approach. We didn't start from conservation of angular momentum as we would have done in the Newtonian approach and applied that to the problem. Instead, conservation of angular momentum emerges really organically from the approach that we're using here. And we'll see that that is actually very, very common for the Lagrangian approach. What extra the Lagrangian approach is going to give us, however, is an interesting interpretation of the conservation laws. These conservation laws originate in a very interesting way in the whole Lagrangian approach. That's going to be subject material for next lecture, bit of foreshadowing, really super interesting stuff that we will learn about the conservation laws that you perhaps didn't know before, or at least hadn't seen the reasons why conservation laws exist at all. Anyway, that's for next lecture. For us, for this lecture, we're going to continue on with looking at some more applications of the Lagrange approach. To do that, I want to draw some lessons from what we have seen in the previous slide. So we'll write down a formal approach for the Lagrange procedure. This is going to be applied only to problems with holonomic constraints. In other words, we're going to have the same number of generalized coordinates as we do degrees of freedom. So there are lots and lots of problems this applies to. What it doesn't apply to are things like a ball rolling on a table, which has a different number of generalized coordinates that are needed to describe its full configuration from as opposed to the degrees of freedom, which are fewer when we're talking about displacements only. We're also going to consider only conservative non-constraint forces. In other words, we're not going to be able to deal with problems involving friction using this particular procedure. But no matter, there are lots of interesting problems that we can certainly attack using what we'll write down here. So the first step in the Lagrange procedure is to write down the kinetic and potential energies using any convenient inertial frame coordinates. So quite often we're going to want to maybe start off in Cartesian coordinates because it's fairly easy to write down the kinetic and potential energies in those coordinates. But in the end, we'll need to, of course, have our generalized coordinates, which really follow the surface that is providing our constraint. It turns out that transforming one into the other is fairly straightforward most of the time, so we'll write down step number 2 as rewriting now our kinetic and potential energies in terms of those n generalized coordinates. Once we have the kinetic and potential energies, we can, of course, write down the Lagrangian, and after that, it's turn the crank. We write down our n Lagrange equations corresponding to n generalized coordinates, and, of course, substitute the Lagrangian and obtain the equations of motion. And quite often we will stop there, or at least perhaps look at the equation of motion and see what we can draw from it just through inspection. Okay, so next problem. We're going to look at a sliding block going down a wedge again, but this time with a little bit of a wrinkle. We're going to allow that block, or sorry, the wedge below it to actually move as well. So both the block can move down the wedge, but the wedge can now move in the horizontal in response to the mass descending down it. We're going to assume here, as usual, that all surfaces are frictionless. Of course, this is needed for our Lagrange approach. Again, both the block and the wedge can move. The question we're asked to answer here is, what are the equations of motion? Okay, so let's apply the procedure that we were dealing with before. First, we're going to write down some Cartesian coordinates, again, because it's straightforward here to write down the kinetic energy and the potential energy in terms of those coordinates, and then we will use our generalized coordinates, which need to match the surface that we're looking at. So let's write down some generalized coordinates while we're at it. We're going to measure the distance that the mass little m is down from the top of the wedge as the generalized coordinate q1. And similarly, from in the horizontal, we will measure the position of the wedge as being the generalized coordinate q2. Now, what I want you to notice here is that because the wedge can move back and forth, the origin for the generalized coordinate q1 actually changes with time. So what we can understand here is that these are generalized coordinates, but these aren't natural coordinates, because the transformation from Cartesians into generalized coordinates is going to have some time-dependent term involved. Okay, so those are our two coordinate systems. We now write down the kinetic energies in this convenient Cartesian system. So the kinetic energies will have the kinetic energy of the wedge being equal to 1/2 m x dot squared. Of course, x dot and q2 dot are the same thing, so I'm just going to immediately substitute in q2 dot for x dot. So the kinetic energy of our wedge is 1/2 big M q2 dot all squared. For the mass of the block, mass little m, we will write down its kinetic energy as being equal to 1/2 m times vx squared plus vy squared, where vx and vy are measured relative to this convenient Cartesian coordinate system. So we have to now re-express those two different speeds, vx and vy, in terms of q1 dot and q2 dot. So let's deal with the block. The block of mass little m, its velocity components relative to the table, in other words, relative to our fixed Cartesian system, will have the horizontal component, vx, being equal to q1 dot times a cosine of alpha plus q2 dot. So in fact, we're summing two different velocities here. The velocity of our mass m as it slides down will of course involve that sliding, but then also we will have the motion of the wedge which it's going to be stuck to. So for Vx, there is going to have to be the the speed in the horizontal of our wedge, and then we're going to add to it in a relative sense the x component of the speed q1 dot. In other words, q1 dot times the cosine of alpha, where here alpha, as always, is going to be the angle that our wedge is making with the horizontal. We now do the same thing in the y direction. It's a little bit simpler because, of course, our wedge is not moving in the y direction. It's only moving along the horizontal. So our mass little m, the block, only has the component Vy being equal to q1 dot projected, of course, into the y direction. So q1 dot times the sine of our wedge angle alpha. Okay, now that we have those, we can write down the kinetic energy for the block. We just take these two terms and substitute them in right here, and we find that the kinetic energy T little m, so the kinetic energy for the block, is going to equal 1/2 m times q1 dot squared plus q2 dot squared plus 2 q1 dot times q2 dot times the cosine of our wedge angle alpha. So you should do those substitutions and verify that what we have here is right. Of course, we're going to have to use the circular identity or the Pythagorean identity to knock out the cosine squared theta and the sine squared theta in favor of q1 dot squared, as we see right here. Okay, so verify that for yourself. At any rate, we can now write down the total kinetic energy. The total kinetic energy T is just equal to T big M plus T little m. Those, of course, are the kinetic energies of the wedge and the block, respectively. We substitute in, and we find the kinetic energy is 1/2 big M plus little m times q2 dot squared plus 1/2 little m times q1 dot squared plus 2 q1 dot q2 dot times the cosine of our wedge angle alpha. And that's it for the kinetic energy. So now we move on to do the potential energy. Of course, the potential energy of the wedge we can just simply take to be equal to 0. It's not going to move in the vertical, so the potential energy there doesn't matter. The potential energy of the block, on the other hand, we will write down as being equal to negative mgy. The coordinate y is going to be measured from the top of our wedge. So we can substitute in then for y and write this in terms of our generalized coordinates. Y is just q1 times the sine of our wedge angle alpha, so this means our potential energy is just negative mg times q1 sine alpha. And with that, we can proceed on to the next step and write down our Lagrangian, which, as always, is going to be equal to t minus u. We substitute in for t, which we have at the top of the page, and for u, which we have halfway down, and that gives us the Lagrangian being equal to 1/2 times big M plus little m times, that will be q2 dot squared. I'm missing a 2 there. I will fix that. Plus 1/2 times m times q1 dot squared plus 2 q1 dot q2 dot cosine of alpha, and then plus mg q1 sine of alpha, where that last term, of course, comes from our potential energy. Okay, the Lagrangian is now obtained. All we have left to do are write down Lagrange's equations and then do our substitutions. So the Lagrange equations for our generalized coordinates will have di L by di q1 being equal to d by dt of di L by di q1 dot. Similarly, di L by di q2 is going to equal d by dt of di L by di q2 dot. Okay, let's deal with these actually in the reverse order. We're going to deal with our equation here, this particular equation first. And the reason why we will deal with this equation first is that if we look at our Lagrangian above, we see that there is in fact no dependence on Q2. That means our left-hand side here is immediately going to go to 0, and that means this quantity here in the brackets is going to end up being a conserved quantity. I wonder which one. Well, let's find out. So, L is independent of Q2, so the second Lagrange equation gives d by dt of di L by di Q2 dot being equal to 0. This means, of course, that di L by di Q2 dot is equal to a constant. We now substitute in for our Lagrangian, and when we do that, the following equation is yielded: m times Q2 dot plus little m times Q2 dot plus Q1 dot times the cosine of our wedge angle is equal to a constant. And this is just an expression of the conservation of linear momentum. In particular, linear momentum in the x direction. Let's see how that comes about. Q2 dot is just going to be the speed that our wedge is moving along in the x direction. So if we multiply the mass times the speed, of course, this gives the momentum of the block, or sorry, of the wedge. The second term here then is going to be the momentum of the block as it's sliding down our wedge. It's just the momentum in the x direction. So to get that, we're going to have the mass of our block multiplied by the speed in the x direction. That speed in the x direction is going to be the sum of the speeds of the wedge plus the relative speed of the block as it's going down the wedge. Of course, just the x component of that, so we multiply by the cosine of the wedge angle alpha. Okay, so momentum is conserved as we maybe should have expected it to. A difference here again is that this really emerges from the whole Lagrangian approach. It isn't something that we start with and then apply it to our problem. It really just pops out of the approach as a matter of course, and we will see this kind of thing time and again with the Lagrangian technique. Okay, so let's take a look at our other generalized coordinate. That's a generalized coordinate Q1. That's measuring the distance of the block from the top of the wedge. Before we do that, let's label this equation here as equation star, because we're going to need that as we're going along. All right, so we substitute the Lagrangian L into our first Lagrange equation. This is the one for generalized coordinate Q1. When we do that and take all the derivatives, it gives little m times g times the sine of alpha being equal to little m times Q1 double dot plus Q2 double dot times the cosine of alpha. Now, really what we want here is an equation of motion just for Q1 double dot. So what we will do is eliminate Q2 double dot using that equation star. So the way we will do that is take d by dt of that equation star and then substitute it into the equation we have at the top. When we do that and rearrange, and you should verify all of this, we get Q1 double dot being equal to g times the sine of alpha times 1 minus little m cosine squared alpha divided by big M plus little m. Now, on the right-hand side, the different parameters that we have there are all constants. So g is just the gravitational acceleration, 9.8 meters per second squared. It's a constant. Alpha is our wedge angle. It's a constant. Little m and big M are constants as well. So what we find is that the acceleration of our block down the wedge is going to be at a constant rate. Okay, so that's nice. That would have been maybe a little bit hard to see in advance. I think that we really should look at this equation a little bit more deeply, though, and make sure that what we've got here is at the very least reasonable. So This equation is fairly complicated. We want to make sure that we haven't made any mistakes and that it fits with our understanding that we could have obtained before from blocks sliding down wedges. So in other words, we're going to look at a few limiting cases to see that they do something sensible. There will be two of them. The first one, A, we will suppose that our wedge angle is going to be 90 degrees. Now remember, we've got our wedge here, and the wedge angle is right there. We're going to open that up so that the wedge angle is 90 degrees. I suppose that that's not technically possible, but in physics we can at least imagine it, or at least imagine a very, very large wedge that is going to have a wedge angle that's approaching 90 degrees. So what do? We substitute that 90 degrees in for alpha in both places. When we substitute it in, the sine, of course, of 90 degrees is just 1. So our numerator becomes just g. In the denominator, we have the cosine of alpha. So the cosine of 90 degrees is 0. So this whole term goes away, and so our denominator becomes 1. So what we find is that in the limit where our wedge angle is 90 degrees, we find that the acceleration of the block down that wedge surface is going to be at the gravitational acceleration constant g. And that makes good sense. If our wedge has a nearly vertical surface for the surface that our block is going to slide on, of course that block is going to accelerate at the normal rate that we would expect for free fall, and that's exactly what we obtained. The other limiting case that we can look at to confirm that our equation is sensible is we're going to take the mass of our wedge to be very, very large. In other words, that wedge is going to be immovable. It's going to be locked there, and our block is just going to slide down that wedge. So if we do that in the equation, if we take big M here to be infinite, then of course this whole term goes to 0. In other words, we're left with Q1 dot being equal to g times the sine of alpha. And in fact, we saw this very same equation earlier on in the course when we were looking at blocks sliding down wedges, but more from the Newtonian point of view rather than from the Lagrange point of view that we're looking down right now. So again, this is just the equation for a block sliding down a fixed incline. And that wraps up that particular example. So let's move on to a new one. So this example will be the example of a bead spinning on a wire hoop. So we'll imagine that we have our hoop right here. We have our mass m. It's just a bead, so it's got a little hole in the middle. So the bead can move up and down along this piece of wire. The circular piece of wire then is then going to be rotating around the vertical axis. So we've got this thing and it's going round and round and round, and that bead has the opportunity to slide up or slide down the hoop itself as it's moving around. This actually is the same kind of problem as you would expect if you had this mass attached by a rigid rod to the origin right here and have the whole thing spin around. So there's a few different configurations that we can imagine. In fact, the configuration that I just described is used or was used for centrifugal governors in steam engine trains. So this was a way of regulating the production of steam driving the engine so it wouldn't, of course, run away. Okay, well, let's look at this particular problem. As usual, we're going to want to know what the equation of motion is. The equation of motion we won't be able to solve analytically, actually, in this case, but through inspection we'll be able to tell quite a bit about the motion of that bead as the hoop is rotating round and round and round. All right, so let's write down a few different parameters that we will be concerned with. We'll imagine that the distance our mass m is from the center of the hoop, in other words, from our origin, is just going to be the radius big R. We will write down the angle that makes with the vertical as being theta. Of course, we're just writing this down in a very similar way to what we might have done for a pendulum. We will also be very interested to know the distance that the mass m is from the vertical line, but in projected there. In other words, we'll be interested in the parameter rho that I've just drawn on the page. Okay, so with this being the case, we follow now the procedure that we outlined before. What we're going to have to do is write down the velocity components, the speed components here, and then use those to determine uh, what the kinetic energy is, and then of course the potential energy. So the velocity components are as follows. Again, we are to first of all consider the velocity components in whatever coordinate system is easiest, and once we have those, then we can write them down in terms of our generalized coordinates. I'm going to consider two different velocity components, or speed components, I should say. We're going to consider the parallel component, which is the component that goes along or parallel to the wire itself. That's just going to be given by the usual equation, which is just going to be r, the radius of that motion as it's going along the wire hoop, times the angular speed, phi dot. Of course, our hoop is rotating round and round and round, and so we're going to have a perpendicular component, so that will be into or out of the page. And that perpendicular component, which we will write down as v perpendicular, is going to equal just the angular speed, omega, times this particular radius, rho. So that's going to be the radius from the axis of rotation. That parameter rho is just equal to r times the sine of theta. So our perpendicular speed is just omega r times the sine of theta. Now that we have that, we can write down the kinetic energy equation. The kinetic energy equation T is going to equal 1/2 m times v parallel squared plus v perpendicular squared. We substitute in for those two different speeds from above, and we find that the kinetic energy T is just 1/2 mr squared times theta dot squared plus omega squared sine squared of theta. Now I want you to notice here that our kinetic energy T is dependent upon the position. And that's not something that we've normally seen before. Normally, when we've written down kinetic energies, we've seen that they've been dependent just upon the speeds. But here we find that, in fact, there is a positional component as well, multiplied by an angular speed for sure, but nevertheless, a positional component that we're not used to seeing. So, of course, we're going to have to account for that when we take the derivatives of the Lagrangian. Okay, so that's it for the kinetic energy. We can also write down the potential energy for our mass m. We're going to do that by first writing down the height of our mass m from the bottom of the hoop. It's just going to be the full radius r subtracting this side of the triangle. In other words, subtracting r, the hypotenuse, times the cosine of theta. So that will give us just this little bit right here, which is our height h. We can factor out r, so we find that h is equal to r times 1 minus the cosine of theta, and that allows us to write down our potential energy function, u, which is always just equal to mgh for these kind of problems, being equal to mgr times 1 minus the cosine of theta. And it's positionally dependent, as always. Okay, given the kinetic energy and the potential energy, we can write down the Lagrangian L, always equal to T minus U for what we're doing right now. It's equal to 1/2 mr squared times theta dot squared plus omega squared sine squared theta minus mgr times 1 minus cos theta. And again, all of the difficult work here is really done. We've written down our Lagrangian in terms of generalized coordinates. In this case, there's only one generalized coordinate. We only need one coordinate to actually describe the motion, and that coordinate is going to be theta. Remember that this is going to be then the angle that our bead makes with the vertical. Okay, so it's going to be that little angle in there. Of course, it's also rotating round and round and round, but it's doing that at a constant rate. So we already know what the equation of motion for that is. It's just going to have v dot being equal to some constant. sorry, phi dot in that particular case being equal to some constant, or omega itself being equal to some constant. Okay, so we write down the Lagrange equation for our one coordinate theta. It will be di L by di phi being equal to d by dt of di L by di phi dot. We substitute in our Lagrangian, take all those derivatives, we find we get m r squared times omega squared sine theta cos theta minus mgr times sine theta equaling mr squared times phi double dot. Again, you should get in the practice of substituting in the Lagrangian and taking these derivatives to verify my work, but just also so that you are just used to the whole process of taking these derivatives. We can now take this equation, of course, and factor some things out and rearrange it. When I do that, I finally get the equation of motion, theta double dot, being equal to omega squared cosine of theta minus g over r times the sine of theta. Now, this is a tricky equation. We can't actually solve this equation analytically. So if we want a solution, you're really in the position of having to solve this numerically. In other words, with a computer. On the other hand, we can inspect this equation and understand quite a bit about the motion just from that. So we're going to proceed on with that as we quite often have done before. So here's how we will do it. Here's how we will proceed. What I want to do is look at the steady state solutions. So we're going to consider cases where the bead is stationary. Now, if the bead is stationary, then its acceleration must be equal to 0. So we can take our equation of motion on the previous slide and set it equal to 0 for these steady state situations, and that will give us omega squared times the cosine of theta minus g over r times the sine of theta as being equal to 0. Okay, so under what conditions can the left-hand side be equal to 0? Well, there are two of them. We could have what's in brackets here be equal to 0, or we could have the sine of theta itself being equal to 0. So let's take a look at that left-hand side first. Sorry, what's in brackets, I should say, first. We will set that equal to 0. Well, when we rearrange it, we get the following. We find that the cosine of theta is equal to g divided by omega squared times r. And again, for the sine theta that follows it, that provides us with another steady state solution. We find that the sine of theta is equal to 0. Now let's look at the first equation of those two. We can, of course, invert that for theta. So we would find one particular solution will have theta being equal to plus or minus the inverse cosine of g divided by omega squared r. Now that equation only holds in certain circumstances. If we return to the original equation here, the cosine of theta has a maximum value of 1. So what we have here, g over omega squared r, is going to have to be less than r. Sorry, it's going to have to be less than 1. So what we can say here is that the solution only holds if the angular speed, in other words, the speed at which our hoop is rotating at, when squared, being greater than g divided by r. So this would be the case of fast rotation. So g over r provides a lower limit for where this particular solution holds. So the solution will hold for any angular speeds, rotation rates of our hoop faster than that. So omega squared will have to be larger than g divided by r. So this will be fast rotation. On the other hand, for sine theta equaling 0, that's going to be a stable solution for theta equals 0, but only at slow speeds. So theta equals 0, of course, will be where the bead is just sitting on the bottom, and it turns out that if our hoop is rotating at very, very slow speeds, that bead is just going to sit there at the bottom. In fact, it will sit there at the bottom until Omega squared is going to be greater than G over R, in which case this will be the new solution. In other words, that bead, while speeds are slow, will be sitting on the bottom, and then when speeds are fast enough, it's going to move up to some position on the side and hold it there in the steady state. There is one other possible solution to sine theta being equal to 0, and that will be having theta equals pi. So if we have our loop, this corresponds to the bead sitting right at the top. Of course, that's always unstable. Any little perturbation, in other words, anything that knocks it off just a little bit, will cause that bead to slide all the way back down to the bottom, or if moving fast enough to some stationary point or some equilibrium point on the side of the hoop. Okay, so those are our steady state solutions. I'm sure you can imagine as well that if we start off with the bead on the bottom and our hoop starts oscillating around until it gets fast enough that our bead will go up to some other position, but in fact it might go a little past it. So in fact, we might expect it to oscillate up and down around that equilibrium position, as these things often tend to do. Okay, and that ends all of the different examples that I had planned for today. So next day, we're going to go on and look at the conservation laws in physics and see what more the Lagrangian approach or the Lagrange approach can tell us about that. And it turns out to be really, really neat. So I look forward to showing that to you in our next lecture. Until then, enjoy. Bye for now.